My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's an absolutely fascinating thing to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out and down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them, and don't want to either.
But Chris doesn't spend weeks away from home and family for the views. Chris and his colleagues at NASA want to answer some pretty big questions by learning more about Alaskan glaciers and how they tick.
You know, why does NASA care about these? Well, they actually disproportionately contribute a large amount to sea level rise.
In the long run, as the Earth warms due to climate change, the big ice sheets and mighty outlet glaciers of Greenland and Antarctica stand to contribute the most to sea level rise, simply because the vast majority of the planet's ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places like Alaska and Patagonia that are contributing about a third of all inputs to sea level rise, even though they account for only 1% of the world's ice.
Mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, these are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICESat-2 satellite and detailed airborne measurements to monitor changing ice.
By the end of the tunnel, you're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and the mastodons. There's sticks that are 40,000 years old. There's grass that's still green, that's tens of thousands of years old.